In any synchronous generator, the most probable insulation failure is between a phase and earth. That's because of the way stator windings are built. Even a small earth fault can quickly escalate, causing burning of the stator core, mechanical stress on conductors, or even fire in air-cooled machines. Once the core laminations are damaged, the generator often needs to be sent back to works for repair, leading to long outages and high costs. That's why a reliable stator earth fault protection is essential, to detect faults early, limit damage, and prevent prolonged downtime. Now that we understand the need, let's see how modern protection schemes detect such faults. For large generators grounded through high impedance, two types of stator earth fault protection schemes are generally applied. 95% stator earth fault protection. 100% stator earth fault protection. In this video, we will focus on the 95% protection scheme, which works by detecting neutral voltage displacement that occurs when a ground fault develops anywhere along the stator winding. But before understanding how it's measured, let's first see why and how the neutral voltage shifts when a fault occurs. We can visualize this using the phasor concept. Under normal conditions, the three-phase voltages VRN, VYN, and VBN are perfectly balanced and spaced 120 degrees apart. Considering each phase with a magnitude of 1 per unit, the vector sum of these phasors is 0, which keeps the neutral point at ground potential. Now, imagine a terminal fault occurs on the R phase of the stator winding. The voltage of the faulted R phase drops to 0, while the healthy Y and B phases rise to line voltage. As a result, the neutral point shifts away from ground potential, producing a neutral voltage displacement. The magnitude of this displacement depends on the location of the fault along the winding. Fault near the terminal, displacement is close to the full phase voltage. Fault near the neutral, displacement is very small, almost 0. Fault in between, displacement is proportional to the distance of the fault from the neutral. The protection relay measures this neutral voltage displacement to detect an earth fault. Now let's see how this is actually measured in practice. There are three practical methods to detect this neutral voltage displacement. Across the neutral grounding transformer, NGT. Across the open delta VT. As derived residual voltage inside the numerical relay. All three methods sense the same fundamental shift, the neutral point moving away from ground potential, but do so using slightly different measurement techniques. In all cases, the displacement voltage detected by the protection relay is of fundamental frequency, 50 Hz or 60 Hz. Let's explore the methods one by one. The NGT method is the most direct way to measure neutral displacement. In this approach, the neutral voltage displacement is detected across the NGT. This measured voltage reflects the neutral to ground displacement, and its magnitude increases as the fault occurs farther from the neutral point. For example, in a 22 kV generator, the phase-to-neutral voltage is 12.7 kV. If the NGT ratio is 22 kV is to 220 volts, a terminal fault produces a secondary voltage of 127 volts. A fault located 5% away from the neutral will generate approximately 6.35 volts at the NGT secondary. To ensure 95% winding coverage, the relay pickup is set around 6 volts, so that any fault beyond the first 5% near the neutral is detected reliably. The NGT method is simple, reliable, and provides direct measurement at the generator neutral. Next, the open delta VT method measures the same neutral displacement, but through phase VTs. Under balanced conditions, the voltages are symmetrical and the open delta output is 0. When an earth fault occurs, the system becomes unbalanced and a voltage appears across the open delta terminals, proportional to the neutral voltage displacement. This residual voltage is fed to the overvoltage relay, which detects the fault. To prevent the relay from being exposed to voltages beyond its safe input range, a specific VT ratio is chosen for this scheme. For a 22 kV generator, the correct ratio is 22 kV by √3 to 110 by 3. Here's why: during a terminal fault, the open delta PT voltage can rise to 3 times the phase voltage, that is, 3 pu. The relay input rating is typically 100 to 120 volts. If a VT ratio like 22 kV by √3, to 110/√3 were used, the open delta voltage would reach nearly 190 volts, exceeding the relay's safe input and risking damage. Using 22 kV/√3 to 110/3 ensures that even under a terminal fault, the maximum voltage at the relay is limited to around 110 volts, keeping it within safe measurement range. For faults 5% away from the neutral, the voltage at the relay drops to about 5.5 volts, ensuring reliable detection. Hence, the relay is configured with a pickup around 5 volts, providing effective protection for 95% of the winding. Thus, the open delta method provides the same fault detection principle, but through phase VTs instead of a neutral grounding transformer. Now, let's look at the third method. Modern digital relays simplify things even further. In these relays, the residual voltage can be derived mathematically from the three-phase voltages using this equation. The resulting residual voltage behaves exactly like the open delta output, providing the same fault detection principle without requiring additional VTs or wiring. The maximum residual voltage during a terminal fault corresponds to 3 times the phase voltage. For a fault located 5% away from the neutral, the derived residual voltage is roughly 9.5 volts. Accordingly, the numerical relay is set to pick up around 9 volts, ensuring 95% coverage. This approach avoids additional VTs and wiring, offering a cleaner, more economical solution in digital protection systems. In actual generator protection systems, the 95% Stator Earth Fault Protection is implemented using 2 redundant numerical relays for high reliability. Here's how it's typically configured. One relay measures the neutral displacement voltage directly across the NGR through the NGT secondary. The other relay measures the residual voltage across the open delta VT connection. The derived voltage method can be implemented in both relays, since all 3-phase voltages are already available in each relay for other protection functions. This provides redundancy and improves reliability of earth fault detection. Let's recap what we learned in this video. 95% Stator Earth Fault Protection works on the neutral voltage displacement principle. In practice, 2 redundant relays use independent inputs, one from NGT and one from open delta VT. The relay pickup setting varies with the method but is typically between 5 and 9 volts, with a time delay of about 0.5 seconds. The 95% scheme ensures robust protection for most of the winding, but the last few turns near the neutral remain unprotected. That's where 100% Stator Earth Fault Protection comes in, using either the Third Harmonic Voltage or the Subharmonic Injection method. To understand how those advanced schemes complement the 95% protection, check out the 2 videos in this series. Together, they complete the story of comprehensive generator Stator Earth Fault Protection.